Question 11. A capacitor discharges through a resistor made of a length of wire. So what they say here is you have a capacitor and this capacitor is charged now. It is a charged capacitor, but you are trying to discharge it through a resistor that is made of a length of wire. So probably your wire should be, let's call this pink thing the resistor wire. Okay, so this might be your circuit right now. And they say that the time constant of this circuit right now is tau 1. Okay, so it takes tau 1 amount of time to reach 1 over E of its initial charge. Okay, that's the definition of time constant. When the resistor is substituted with another wire made of the same metal but of twice the diameter and twice the length of the first wire. Okay, there's many things being mentioned here. We are substituting it with another wire, then this wire is made of the same metal, twice the diameter, twice the length of the first wire. The time constant of the new circuit right now is tau 2. Okay, so should I draw it again? Yeah, probably I can just draw it. Okay, so I have a capacitor, then this capacitor right now is being connected again to a wire, but this time this wire here should probably be much larger than before and should be much longer than before, something like this. Okay, yep. Okay, so that's the new circuit right now. Then the amount of time to the time constant right now is tau 2. Okay, so now they ask for the ratio of tau 2 to tau 1. What is it? Well, we know that tau is just RC. For this case, they don't mention any change to the capacitor, so I believe the C will remain the same for both situations. But the R, I think it's quite obvious that they are changing the R right now. So we'll call this one R2, we'll call this tau 1, the resistor, we'll call it R1. Okay, so let's try and determine the new R and the old R. Okay, for R, to determine the resistance is just resistivity times length divided by area. Okay, this is what you learn in chapter 3. Actually, you are bringing some knowledge that you learned from chapter 3. Okay, so we are now comparing it to a new situation. Usually I will just call it R1, I will just usually call it R prime, but since I label it as R2, I might as well just call it R2. But right now I'll call this rho 2 L2 over A. Let's just call this rho 1 L1 and A1. Okay, we know that rho 2 is equals to rho 1 because they say it's made out of the same metal. Okay, in that case rho 2 will be equals to rho 1. I can just write it as rho 1. Length 2 is twice the length of the first wire, so we can substitute length 2 to become 2 times of length 1. Okay, the next thing that they mention is it's twice the diameter. If it's twice the diameter, then d2 will be equals to 2d1. We also know that area 2 is equals to pi r2 squared. That means by it's pi d2 over 2 squared. Okay, so that means by our situation here will be pi 2d1 over 2 squared. So 2d1 you can just cross it out, so it becomes pi d1 squared. So this is for A2. If you compare with A1, A1 is just pi r1 squared, which is just pi d1 over 2 squared. So now this will become 1 over 4 pi d1 squared. So we know that A2 is actually 4 times A1, because if you take A1, 1 over 4 pi d1 squared, You multiply by 4, then that's what you get, pi d1 squared. So A2 is equals to 4A1. We can substitute that inside. So it becomes 4A1. So now we can change this a bit. Bring up the constant in front, then you're left with rho 1 L1 over A1 at the back. Rho 1 L1 over A1 is just R1. So now you know that it's half R1. Okay, you are bringing what you have observed here for R1. What you're doing it is you are substituting it to R2. Okay, so you have built the relationship that R2 is equals to half of R1. So now how will you find the relationship between tau 2 and tau 1? Well, it's relatively simple. Tau 2 over tau 1 is just equals to R2C divided by R1C. You know that R2 is half of R1 divided by R1, then we cross out the C already, so we are left with half. Okay, so what does it mean? It means by tau 2 to tau 1, the ratio should be equal to half and 1, which can be also equal to 1 and 2. Okay, if you multiply this by 2, if you multiply this side by 2, yeah, then the ratio is still the same, 1 to 2. In that case, we'll pick our answer as 1 to 2. Okay, so greater resistance causes greater time constant. Lower resistance causes lower time constant. Okay, so that's the idea behind it. That's all for question 11. So as you can see, we know that the relationship between time constant, resistance, and capacitance is tau equals to RC. So as we can see in figure 2, the circuit number 2 here has a lower resistance because R2 is half of R1. The main reason is being it having a greater cross-sectional area. But the conclusion is if you have a lower resistance, it will cause you to have a shorter time constant. You have a smaller time constant, that means it takes a less amount of time for you to discharge, or it takes less amount of time for you to charge to a certain value. Okay, so that's it for question 11. Question 12. A parallel plate capacitor is charged by connecting it to a battery. Okay, so this capacitor is now being charged. The energy stored in the capacitor is U0. Okay, so after being charged, you store an amount of energy U0 in the capacitor. With the battery still connected, okay, this is very important. With the battery still connected, to the battery, the space between the plates is filled with an insulator of dielectric constant 4.0. So this dielectric constant is mu0R equals to 4.0. Okay, so this is also an important point. You're filling the space in between the plates with an insulator. Okay, what is the energy stored in the capacitor? Okay, so now they want you to express the new energy stored in the capacitor. Let's just write it for the old case first. For the old case here, U0 is just equals to half CV squared. Okay, let's write it the original version, half CV squared. But for new situation here, U prime, you have a new capacitance because you insert dielectric, and we are not sure if this V here will change as well or not. Okay, so let's find it out. So capacitance, we know that the capacitance will definitely increase because we know that the dielectric constant is equal to 4.0. And because we know that dielectric constant is just the ratio of the capacitance with dielectric over the capacitance without dielectric. Okay, in this case, let's change it. That's a formula, but for in our case, we call it C prime over C. Okay, C prime has dielectric. Without prime, there's no dielectric for this specific case. Okay, so we can see here that because this is equal to 4.0, we know that the new capacitance will be 4 times the old capacitance. So we can substitute that in 4.0 C. How about the potential difference across the capacitor? Well, I've mentioned the keyword. The battery is still connected. So what does it mean is the V must be constant. The V should not change because the battery is supplying a fixed amount of energy, and that energy must be supplied to the capacitor. Okay, so your V should not change. In that case, your V should be constant, so V prime will be equals to V for this case over here. So you can just replace this V prime here with V squared. So now we may see that this will be 4.0 times half CV squared, which we can change it to become 4.0 times U naught. Okay, so for this case, our answer will be C. So if you are connecting your capacitor to a dielectric, you're connecting your capacitor to a battery and you insert a dielectric into it, what will happen is there will be more energy being stored in the capacitor. So that's the situation if you connect the capacitor to a battery. Increase in the energy being stored in the capacitor. That's all for question 12. Question 13. All the capacitors in the arrangements below are identical. The effective capacitance between X and Y is the least in... Okay, I'm sorry with the small picture, but as you can see here, most probably you can see, there's 4 capacitors in A, B, C, and D. All of these combinations here are made out of 4 capacitors, just that they are being connected differently. Okay, let's find out which one of them has the least effective capacitance. Let's start with A. Okay, A here has 4 capacitors being connected in series. Okay, so we know that if it's capacitors connected in series, to find the equivalent capacitance, let's call it C prime. Okay. The effective capacitance here is just 1 over C plus 1 over C plus 1 over C plus 1 over C. I call all of the individual capacitance to be C because they are all identical. There's no need for me to label it as C1, C2, C3, and C4. Just label everything as C, whereas the equivalent capacitance, we call it C prime. Okay, let's just don't call it C prime. How about we call it CA? Okay, the capacitance for combination in option A. Okay, so now this will be 1 over 4 over C, and that will be C over 4. Okay, so that's for option A. For option B, you have a wire here, then you have a junction breaking it into 2 routes. For each route, you connect 2 capacitors in series. This is the arrangement for section B. So if you find the capacitance for B, what we need to do is we need to find out the capacitance for this portion over here first. This portion over here is just 1 over C plus 1 over C. So with that being found, we can times it with 2, or we can just plus with another set of the same thing, because now we are combining these two series combination together. Okay, so this will be this part, whereas the yellow series combination will be this part over here. Okay, so if you work it out the maths, you should end up with C over 2 plus C over 2, and that will be equals to C. Okay, for option C, it's a bit different. You first have something connected in series, then branching off into 2 different parallel routes. For each route, you put in 1 capacitor. Then once you connect the 2 routes back into 1, you have a last capacitor connected at the back. Okay, so to find the effective capacitance for this combination, what can we do is, we know that it will be 1 over, there will be 3 groups that we need to add together in series. Group 1, group 2, and group 3. Three of them we have to add together. So the first one will just be 1 over C, but the second one will be 1 over, you need to find the effective capacitance and put it down here. The effective capacitance is just C plus C because you are combining two capacitors connected in parallel. Okay, the last one will be 1 over C. So to do that, we will end up with something like this: 2 over 2C plus 2C over 1 over 2C plus 2 over 2C, sorry. So you end up with 2C over 5. Okay. The last option D here, it's you have something like this. Okay, I think I'll just skip the description. I'll just draw it out. Okay, something like this. So in order to find the capacitance for option D, what can we do here is to add these two things up, add these two series combination up first. So I believe it's the same for this part. Then only later we will combine them, these two things in series. There's a parallel combination, which is C plus C. So it's in series right now, so it will be 1 over C plus C plus 1 over C plus C. Okay, this 1 over C plus C here, it's combining this C plus C over here. Okay, let's do it step by step. The C plus C over here represents connecting two capacitors in parallel. That's like what I've labeled in dashed yellow lines over here. So once I've found it for this part and this part, what I do is I combine them in series using the 1 over C plus 1 over C idea. Okay. If you do it slowly, you'll find out it's the same thing. Okay. I hope you all can try to figure it out. So if you bring them together, you end up with 1 over 2 over 2C, and that will be equals to C. Okay, so with that said, I think the effective capacitance which is least will be, which one? I think it's A. Okay, 1 over 4 is smaller than 2 over 5. Okay, so that's all for question 30. Oh, before we move on, if we add capacitors together in series, the effective capacitance or the equivalent capacitance will be decreasing. If you add the capacitance in parallel, if the capacitor are connected in parallel, then the capacitance will be increasing as you just sum them up. Okay, so that's the idea behind connecting capacitors in series and parallel. That's all for question 13. Question 14. A resistance and a capacitors are connected to a voltage V as shown in the circuit. When the current in the circuit is I, the charge on the capacitor is Q, the voltage is, okay, so as you can see here, there's a resistance and a capacitor, and they are both connected to a voltage, or we call it a power supply V as shown in this circuit over here. So the current that is flowing through the circuit, we name it as I, whereas the charge that is being stored in the capacitor, we name it as Q. And now they ask us to find how to express V in terms of I and Q. Okay, so V here represents the voltage of power supply, and as you can see in the answer choices over here, we are supposed to express this V here in terms of the current I and the charge on the capacitor Q. Okay, so to do this question, you have to recall something that I have explained in some other videos, earlier videos, or from class. Okay, this V here represents the voltage of the power supply. Okay, so when we have a series circuit consisting of a resistor and a capacitor, so the voltage of the power supply here will actually be divided to be given to the resistor or to the capacitor. Okay, and if you sum up the voltage across R and the voltage across C, what you see is the sum of these two things will be equal to the voltage of the power supply. So in mathematical form, that will mean by V is actually equal to VR plus VC. The voltage across the resistor plus the voltage across the capacitor will be equal to the voltage of the power supply. Okay, so what's after that is we know that voltage across the resistor is just V equals to IR. This one is from chapter 3. V equals to IR is for any ohmic conductor. So in this case, this resistor here is ohmic conductor, so it behaves that way. Then V for capacitor, we know that we can express it in terms of charge and capacitance using the idea of Q divided by C. Okay, so with that said, we know that V is actually equal to IR plus Q over C. Okay, so as you can see, the answer here will be this one, IR plus Q over C. Okay, so it's important to know that the voltage of a power supply will be split to the resistors and the capacitance if they are both connected in series. Okay, so that's all for question 14. Question 15. The capacitance of a parallel plate capacitor can be increased. Okay, without looking at the answer, you should be able to recall that there are only 3 ways to change the capacitance of a parallel plate capacitor. Okay, the capacitance can only be changed by changing some stuff of the capacitor itself. You cannot change the capacitance by changing something within the circuit. Let's say you want to increase the voltage of a power supply. That is changing the circuit. You are not doing any particular changes to the capacitor itself. So if you are not making changes to the capacitor, you can't change its capacitance. Okay, capacitance here, okay, since many of you asked this question, I might as well explain it here. C equals to Q over V here. This C here is supposed to be a constant of proportionality actually. Okay, constants of proportionality, and it's the constant of proportionality between charge and potential difference. Okay, you can, if you rearrange it, then probably you see Q equals to CV, right? You can think of it as being similar to F equals to Kx for Hooke's law. Okay, in Hooke's law you learn F is equal to Kx, like Kx, right? Okay, so if you increase the force, the K will not change. The K will remain constant actually. Okay, so what change is actually the displacement change. Okay, it works the other way around as well. Let's say today you increase the displacement of a spring, you stretch the spring or you compress the spring. What change here is not the spring constant. What change here will be the force that you exert on the spring. Okay, the greater the change of displacement, the greater the force you need to exert on the spring. So that's Hooke's law. So K is spring constant. Okay, so how do you really change spring constant here? Is by changing the diameter of the spring, or you can change the length of the spring, or you can change the stiffness of the wire used to create the spring. So those are things that you are changing directly onto the spring itself. Then those will change the spring constant. Okay, when you increase the force, you can't change the spring constant. When you increase the displacement, you can't change the spring constant. Okay, you can change it only by changing the spring itself. Okay, so for this case, right, the capacitance here can actually be changed by only changing something with the capacitor itself. So this thing is capacitance. If you want to change something with the capacitance, what should you change is you should change the area of the parallel plates, or you can change the distance of separation, or you can change the you can add in dielectrics in between the parallel plates. Okay, so dielectrics can also be an option. Okay, so I hope you see that changing the circuits will not change anything about the capacitance. To change the capacitance, you need to do something directly to the capacitor. Okay, so what governs capacitance is actually this formula over here. mu naught R, mu naught not A, mu naught, sorry, epsilon R, epsilon naught A over D. Okay, usually the epsilon R is not there, but to show the effect of dielectrics, this will be dielectric constant. So you change this by inserting dielectric constant of different permittivity. Different permittivity, then you have different dielectric constant. Okay, this one will be the area, then this one will be the distance between the two plates. Okay, so I hope we are clear with this. What changed, what kept constant, these are very important. So now let's look back to the question here. Option A, by increasing the potential difference between the plates, that is changing something regarding the circuit. You are increasing the voltage supplied by the power supply. So those are changing circuit, it will not change the capacitance, no. Next one, by increasing the charge on the plates. Okay, that is also changing. By increasing the voltage of power supply, essentially increase the charge, but the capacitance should not change. Okay, next one, by increasing the separation between the plates. So if you increase the separation between the plates, you are increasing D over here. If you increase the D, what will happen is the C will actually decrease, the capacitance will actually decrease. That is opposite of what we want to find, so this should be wrong as well. And the last one is by using a dielectric with higher permittivity. Higher permittivity means by your dielectric constant will be greater. If that's the case, your capacitance will increase. And that's the effect that we are looking for. So our answer will be by using a dielectric with higher permittivity. Okay, so that's all for question 15. Question 16. Two parallel plate capacitors are connected in series to a battery. A slab of dielectric is then inserted into one of the capacitors. Which of the changes described below is correct? Okay, so if you would like to draw the situation out, the situation will have two parallel plates capacitor, and these two parallel plates capacitors are connected in series. Okay, so I draw them. Everything has to be in one loop, and this is in series with a battery. So it means these two capacitors here are actually charged already. Okay, so they are connected to a battery in series. Okay, a slab of dielectric is then inserted into one of the capacitors. So let's say we put a dielectric into this capacitor over here. Okay, then they ask which of the changes described below is correct. Okay, so to analyze this situation here, let's label everything down first. We know that this is the voltage of the power supply V, then there will be C1 over here, C2 over here, and because they are charged, they should have V1 over here, V2 over here. These are the potential difference across the capacitor. And of course, you need when you have potential difference for across the parallel plate capacitor, is due to charge being stored at this capacitor itself. Okay, so let's try and determine some of the relationship here. Okay, one of the way for us to really understand this relationship here is to combine the two resistors in the two capacitors here in that are in series right now into one single equivalent capacitance. Okay, so we want to convert it into a single capacitor, something like this. Okay, so we call this, just call this as C itself, and of course the V over here will be equal to the power supply, because there's only one battery, and this battery is only connected to one component, which is the capacitor. So the V supply will be equals to V capacitor. Okay, so let's try and write down all the things we know. C here, which is the equivalent capacitance, can be determined by 1 over C1 plus 1 over C2. Okay, so that is our capacitance. And what else do we... Okay, so let's try and determine how the capacitors change when we insert the dielectric. When we insert a dielectric inside this capacitor 1, what will happen is the capacitance of capacitor 1 will definitely increase. Okay, but this increase in capacitance 1 actually causes a decrease to this portion of the equation. Okay, 1 over C1 here actually decrease. But if you look at everything in overall, then here should be a decrease. But since this is below the fraction, eventually it will cause the capacitance, the effective capacitance, to actually increase. So the effective capacitance is actually increased. So actually we have our correct answer. Our correct answer is the effective capacitance is increased. But let's look at the other options and try to prove that they are wrong. First thing, the total charge on both capacitor is reduced. Is it true or not? If you look at this case over here, we know that C, the effective capacitance here, will be equals to Q over V. Okay, we know that V is constant because you're connecting it to a battery over here. There's only one battery and you don't change anything to this battery here, so the V here should be constant. But you have proved down here that the equivalent capacitance actually increases. So with the increase of equivalent capacitance, the charge should also increase as well. So the total charge on both capacitors should actually increase, not reduce. Okay, increase. Okay, how about the other option? The total energy stored is reduced. So how should we determine the total energy stored for this case over here? We can determine it using U equals to half QV. So if we use this equation here, we know that V is constant, and we know that Q is actually increasing. In that case, we know that our energy should actually increase as well. But over here, it mentioned that it's reduced, so that should be wrong. It should be increased. Okay, last one. The potential difference across both capacitor is increased. Nope. As we have mentioned here very clearly, because you are connecting it to a battery, you cannot change the potential difference. So the potential difference should be remain constant. Oops, I crossed out too much stuff. Both capacitors remain constant. Okay, so the answer for this question here will be the effective capacitance is increased. Okay, so that's all for question 16. Question 17. 4 identical capacitors, each of capacitance C, are connected as shown below. In which arrangement is the equivalent capacitance C? Okay, so each of these capacitors here, there are 4 capacitors in each diagram here. Each of the capacitors should have a capacitance of C. And now the question asks, what kind of arrangement gives you back an equivalent capacitance of C again? So it means by the equivalent capacitance should be the same as the capacitance of one single capacitor. Okay, so let's look through each of the options here. For option A, you have 4 capacitors being connected in series. Okay, so how should we find the capacitance, the equivalent capacitance? You can find it using again the equation for capacitance in series. That's 1 over C plus 1 over C plus 1 over C plus 1 over C. And if you work through the maths, you find that the answer is C over 4, which is not our answer, as we want our equivalent capacitance to be equal to C. C over 4 is not C, so A is not the answer. B. So you have a connection, first single capacitance, then you branch into 2 routes, with each route having 1 capacitor, then you converge back to a single path, but now this single path consists of 1 capacitor again. So to determine the capacitance for combination B over here, what can we do is, we know that there will be 3 components that we add up in series. This is one component, this is the second component. Okay, let me use different color. Second component will be this, the third component will be this. So of course later you have 1 over something plus, then you will have another 1 over something, then you plus, then you have another 1 over something. Okay, we know that the yellow one is just C, the blue one is just C as well, so you can write it down first. But how about the things in the middle? So for the middle, the green area over there are two capacitors being connected in parallel. So if you want to combine two capacitors in parallel, you just need to sum up their capacitance. So it just means that here it will be C plus C. Okay, so again, we can proceed to do the maths. Then you end up with something like 2 over 2C plus 1 over 2C plus 2 over 2C. Then you end up with an answer of 2C over 5. Well, that's not our answer as well, because that CB is not equal to C. Okay, let's move on to option C. Option C, you have capacitors being connected through two parallel branches, two sets of parallel branches. The first set consists of one capacitor for each branch. The second set consists also of one capacitor for each branch. Okay, so all of these capacitors are identical. So if you want to find the capacitance for figure C here, you have to add up two things in series. One will be this part. The second one will be this part. Okay, so if you want to add them on, you add them on in series. There will be two components to add on. One will be 1 over C plus C. The other one will be plus 1 over C plus C. Okay, why is it C plus C? Because these two capacitors here are being connected in parallel. So if you want to find the combined capacitance, you just sum their capacitance up. So once you reach this part, you find that this will be 1 over 2C plus 1 over 2C. So if you add them up, flip the things, then you'll be equal to C. And this should be our correct answer, which is C. But let's look through everything to be confirmed of everything. So let's look through D again. D, you have a capacitor followed by two branches. One branch has two capacitors. The other branch has only one capacitor. So you converge back into a single current route. Okay. So CD here, you have two components to add in series. One will be this component. The second one will be this component over here. Okay, so you are adding them up in series. So I expect something like 1 over. Then you have 1 over C. Then you also have 1 over something. Okay, so you need to find the resistance, you need to find the capacitance for this part, and you need to find a combined capacitance of these two branches. Okay, so if you like to add them up, I believe this one you can add them up as C, but the next one you have to find it through another set of 1 over C plus 1 over C. Okay, I suggest you to do it step by step, because sometimes I'm a bit short of time, so I'll just do things in a slightly shortcut way. Okay, so 1 over 1 over C plus 1 over C here, you're actually finding the combined capacitance over here. Then you sum them up with this branch of the capacitance. You sum them up in order to find the combined capacitance across these three capacitors. Then after that, you sum them in series again using this 1 over thing. Sum up with this blue capacitor over here. Okay. I highly suggest you to do it on your own to figure out everything by yourself. Okay. But this will be 1 over C plus 1 over C plus C over 2. Okay. So if you proceed to calculate everything, I believe the answer should give you 3C over 5. Which is of course not our answer as well. Okay, so we have confirmed that the answer should be option C. Okay, so the steps is still the same. You just need to know how to combine them to find the equivalent capacitance. Combine them step by step is fine. Okay, it's actually highly recommended that you do it step by step instead of just combine everything in one equation. Okay, so that's all for question 17. Question 18. A parallel plate capacitor is charged using a battery and the battery is then removed. Okay, is removed means that it's no longer connected to the battery. Then after that, only a piece of dielectric is inserted in between the plate of the capacitor. You first remove the battery, make it charge isolated or electrically isolated, then only you insert the piece of dielectric. Okay, it's important to know that. So they ask for the change in the capacitance and the energy stored in the capacitor. Okay, so let's draw the situation here first. So you have a charged capacitor. Just call one side positive, the other side negative. And this capacitor here is no longer connected to a battery because the battery is already removed. Okay, so at this stage right here, it has a charge of Q and it has a potential difference across them of V, is charged already, and the capacitance is just C. Okay, but once you have inserted a dielectric inside it, one thing that you know for sure is that the C will definitely increase due to this insertion of dielectric. Okay, so with that said, we will know that in capacitance actually must increases. So anything with decreases is already wrong. Okay, so the next thing that they ask for is the energy stored. Okay, to determine the energy stored, we know that there's three formulas which are actually equivalent each other. There's half CV squared, and there's also Q squared over 2C, and there's also half QV. Okay, to use which equation here, it's actually something that you really need to think carefully. One thing to think carefully is what is kept constant in this situation. Okay, as you have seen here, this capacitor here is electrically isolated. Charge cannot go in from anywhere because outside here is just air, there's no loop. Charge cannot get to the positive plate, the charge cannot get to the negative plate. It's just trapped there. So the Q must be constant. Why is it important to know that Q is constant? Because it allows you to use equation that can determine the relationship with energy more efficiently. Okay, the idea is if Q is constant, you should use the equation of U which has Q inside of it. In that case, you can use either U equals to Q squared over 2C, or you can use U equals to half QV. Why these two equations are more recommended compared to CV squared is, if you have one thing constant, in this case the Q is constant already, it's easier to track the change of U because there's only one thing that is changing, which is either the C or the V. Okay, in this case, I think it's very pretty obvious. We know that the capacitance actually increases, so that will cause the energy to actually decreases. Okay, so this is the relationship between the capacitance and the energy stored. Okay, but you can also do it step by step. You can do it using C is equals to Q over V, and because we know that it's electrically isolated, then Q should be constant. So if the capacitance happen to really increase, then it must be due to the decrease of V. So if V is decreasing, then of course we know that U should be decreasing. Okay, there's many ways to get around it. It's just that if you use the equation which has one thing being kept constant, and you have left with one thing to which you allow to change, then to figure out a relationship will be easier. Okay, so in this case, the U, the energy stored, actually decreases. So anything with increases should be wrong. Increases wrong. Okay, so in that case, we know that our answer should be capacitance increases, energy stored decreases. Okay, so that's all for question 18. Question 19. Two capacitors C1 and C2, which are connected to a switch S, are shown in the diagram below. The capacitor 1 is charged, while capacitor 2 is uncharged. Let me write down here. Capacitor 1 is charged, capacitor 2 is uncharged. Okay. When the switch S is closed, what happened to the total charge in the capacitors C1 and C2? The potential difference across capacitor C1 and the total energy in the capacitors C1 and C2. So they ask for three specific things that we need to investigate now. Okay, so C1 here, capacitor 1 here is actually charged already, so there might be charges around here. Okay, opposite charge. So what happens is when you connect the circuits by closing the switch S over here, some of the charges will move from the charged capacitor to the uncharged capacitor. So over here at capacitor 2, you gain some charge over here, while in capacitor 1 here, you lose some of the charges. Okay, so this is what might happen. Okay, the whole process here will continue until a stage where the potential difference across C1 and the potential difference across C2 should be the same. Okay, it should stop at the moment where V1 here, new V1 here will be equals to the new V2 here. Okay, then the process of losing charge and gaining charge will stop. Why does V1 prime has to be equal to V2 prime? Is because if you have potential difference, charge will flow. In order to not have charge flowing, you have to have zero potential difference. So if the left plate and the left plate of C1 and the left plate of C2 wants no charge to flow between them, the potential difference between the left plate of C1 and the left plate of C2 must be zero. There's no potential difference across these two left plates. Then only charge will not move. Okay, the same for the right hand side. The two right hand plate here should have zero potential difference across them. So charge will stop flowing. So if the potential difference of the left plate for both left plate is the same, and the if the potential for both left plate are the same, and the potential for both right plates are the same, then the potential difference between the left plate and the right plate for both capacitors should also be the same. That's why V1 prime is equal to V2 prime. Okay, so those are the information that we know. So let's try and write down everything that we know. Okay, the initial situation here, let's write it clearly. The initial situation here, you see that C1 is equal to Q1 over V1, whereas C2 is equal to Q2 over V2, but because C2 is being uncharged, so Q2 and V2 will both be equal to 0. Okay, the final situation that we will witness will be C1 will be equals to Q1 prime over V1 prime, whereas C2 will be equals to Q2 prime V2 prime. I didn't bother to label prime on C1 and C2 because we know for sure that C1 and C2 will not change. It's because you don't change anything directly on the capacitor. You're not inserting a dielectric, you're not increasing a distance of separation, you are not increasing a surface area. Okay, you're doing nothing directly to the capacitor. Okay, so in this case C1 and C2 will be the same. Okay, so once we have reached this part, what can we move on is to find, since this switch S here is already closed, then this loop is officially a closed loop now. So if it's a closed loop, I think it's doable for us to find the effective or the equivalent capacitance. Okay, so for equivalent capacitance, we emphasize that just now v1 prime should be equal to v2 prime. So if v1 prime is equal to v2 prime, this is more like a parallel connection. So if it's a parallel connection, then you see C prime, the new equivalent capacitance, should be equals to the sum of C1 and C2. Okay, this formula is valid for parallel combination of capacitors. And now since we see that V are the same for both capacitors, this is more like a parallel combination of capacitors. Therefore, we use the equation for capacitance, which for two or more capacitor connected in parallel. So this is the formula. Okay, then what else do we know? We know that V1 prime is equal to V2 prime, and just let's call them as V prime. Okay, we learn about capacitance, we learn about voltage. How about the charge? Okay, the new charge over at Q1 and the new charge over at Q2 is supposed to be the same as the sum of charges at the initial condition. Okay, because this is due to conservation of charges. Initially you have how much charge, now you're just redistributing it across two different capacitors. Before that, everything is at one capacitor, capacitor 1, but now it's being distributed over capacitor 1 and capacitor 2. Okay, we know that capacitor 2 initially has no charge, so Q2 should be equal to 0. So Q1 prime plus Q2 prime equals to Q1. So these are some of the relationship between the capacitance, the potential difference, and the charge stored on the capacitor. So we are asked to find the total charge in capacitor C1 and C2, and I have said just now, this one will tell us that the total charge does not change. Okay, the total charge, no change. Because initially you have how much, and that's how much you distribute between the two capacitors. So if you sum the charge stored at each capacitor back up, you get back the initial charge stored at one capacitor. Okay, the potential difference across capacitor C1. Okay, to understand that, I think it's better that we find the relationship between V first. Okay, so the new V, whether it will be greater or it will be smaller than the initial V across C1, let's try to find out. The new V is called V prime. Okay, so how would we get this? How do we get V prime here? Is we need to use an equation that connects the old and new situation. I believe this is a good equation for us to connect between the old and new situation. So let's try and use this formula. Q1 prime plus Q2 prime is equals to Q1. So we know that Q1 prime is equals to C1 V1 prime plus C2 V2 prime. And Q1 is just equals to C1 V1. We know that V1 prime is equals to V2 prime, and we can call them commonly as V prime. So what can we do is we can factorize out V prime and left it with C1 and C2 inside the bracket. Here will be C1 V1. Okay, so now we can build a relation between the initial potential difference and the final potential difference. The final potential difference here, which is V prime, is just equal to C1 divided by C1 plus C2 times V1. Okay, we know that if C1 divided by C1 plus C2, this coefficient over here should be smaller than 1. Okay, it's something like a potential dividers concept. So it's smaller than 1. Okay, so what kind of conclusion we can build is that V1, if V prime will be smaller than V1. Okay, so if V prime is smaller than V1, what does it tell us is the potential difference across capacitor 1 actually decreases. Okay, this V prime here is the V of 1 prime and the V of capacitor 2 prime. Okay, so essentially we can say that V1 prime is smaller than V1. So the potential difference across C1 actually decreases. Okay, so I think we have done quite a great job. Total charge, no change. This is correct. This is correct. This is wrong. This is wrong. So this one is decreased. This one is decreased. Okay, so we have reached the last stage, which is to determine the total energy in capacitor C1 and C2. Okay, so let's try to find the initial, then after that we find the final. So for initial, which is U, then it will equals to half Q1 V1 plus half Q2 V2. Okay, that's the initial situation. But since capacitor 2 is not storing any charge, we know that this will be 0, so our initial energy stored will be half Q1 V1. How about the new energy stored, U prime? New energy stored here, it can be found by using half Q1 prime V1 prime plus half Q2 prime V2 prime. We know that V1 prime and V2 prime are just equal to V prime, so we can bring out V prime. Then you're left with Q1 prime plus Q2 prime. Q1 prime plus Q2 prime is equal to Q1. So you're left with half Q1 V prime. Okay, so let me write down the initial and the final. The initial is half Q1 V1. The final is half Q1 V prime. And since we know from here that V prime is smaller than V1, therefore we can know that let's bring this over. Because we know this and we know that, we can arrive at the conclusion that U will be greater than U prime, which essentially means the total energy actually decreases. Okay, so we derive this total energy decreases based on the fact that the potential difference across C1 decreases. Okay, so V prime is smaller than V1. V prime is smaller than V1. That's why U prime is smaller than U. So if U is greater than U prime, then it means by the total energy actually decreases. Initial bigger, final smaller, decreases. Okay, so from here we can see that no change will be wrong, and total energy in capacitor C1 and C2 will decrease. We know that our answer will be this one. Total charge, no change. Potential difference across C1, decrease. Total energy in C1 and C2, decrease. Okay, so that's all for question 19. Question 20. A piece of dielectric which is placed between two plates of a charged parallel plate capacitor is shown in the diagram below. So I have a piece of dielectric and it is placed between two plates of a charged parallel plate. So this is a capacitor which is being charged and you insert dielectric in the middle of it. Okay, so the distance between the plates is D. Okay, so I assume here it will be a graph something like this. A straight line. Let me draw a straight line first. Okay, then this straight line here, X. Then I believe this is the distance 0 and this will be D. And they ask you to find the variation of electric field strength E in distance X. Okay, so electric field strength E is something that you learn from chapter 1, electric field strength created by a parallel plate. Okay, so we know that if we have two oppositely charged plates, in this case they have the same amount of charge, just oppositely charged, what will happen is you create a uniform electric field. That's the first thing created. You create a uniform electric field. Okay, let's draw the arrow like this. Okay, so now we have a dielectric in between here. So what is the effect of this uniform electric field on the dielectric is it will induce a surface charge on the surface of the dielectric itself. I will represent it in pink maybe. Okay, so you have a oppositely charged induced. Okay, let's say over here, and over here. Induce a negative charge on the surface of the dielectric which is near the positive plate. You induce negative charge on the surface which is near the positive plate. And of course, you induce a positive charge on the surface which is near the negative plate. Okay, so with that being said, we know that there's negative and there's positive. Of course, you can also create an electric field. But this time the electric field will be in the opposite direction. In the opposite direction because the plus is now on the right and the negative is now on the left. Okay, so because you have an electric field which is in the opposite direction, essentially you can think of it as the two opposite direction electric field cancel each other out. So essentially you might see something like this. They sort of cancel out. Okay, if I cancel, I should probably remove the induced charges as well. So something like this. Okay. So if that's the case over here, we can see that there's less amount of arrow in the dielectric compared to out of the dielectric. Okay, so what kind of conclusion can we make here is if we can see more lines over here, it means the density of electric field lines is greater. Density of electric field line is greater means by the E is greater over here. Okay, the magnitude of the electric field is greater over here. The magnitude of the electric field is greater over here. But within the dielectric, the electric field is bigger over here. Okay, another thing that we observe is the number of electric field lines that I draw over here will be the same with the number of electric field lines that I draw over at the right hand side. So the left hand side and the right hand side of the dielectric share the same magnitude of uniform electric field. So with that said, I believe you will see probably see something like this. You will see a high magnitude of electric field over at this region and this region, whereas within the dielectric itself, you'll probably see the electric field to be much weaker compared to outside the dielectric. Okay. So the axis should be shift downwards. Okay, let me shift the axis downwards. Okay. So this should be the graph that we will be drawing. 0 x. Okay, so if you compare it with the graph that we have here, I think the correct answer should be C, which shows something like a square wave kind of shape. Okay, something like a castle shape. Okay, so that's for question 20. Question 21. Two charged capacitors, each of capacitance C, are discharged using the circuit shown, which contains two resistors of the same resistance R, and they ask for the time constant of the circuit. Well, this question should be relatively straightforward. We know that time constant is equals to RC, so we need to find the R effective, the effective resistance, and we need to find the equivalent capacitance. So how do you find the effective resistance? We see that these two resistance here are two resistors here are being connected in parallel. So if you want to find the effective resistance, you use 1 over R plus 1 over R. Whereas for capacitors, the two capacitors are connected in series. So if it's in series, to find the effective equivalent capacitance, the formula should be almost identical in structure to the one that we have used just now. Okay, the structure should be similar. So now if we move around, manipulate the algebra, then you have R over 2, and you multiply it with C over 2. In that case, you create the time constant, which is 1 over 4 RC. In that case, our answer should be A. This one, the first one, 1 over 4 RC. Okay, so that's it for question 21. Question 22. The circuit shown is used to charge a capacitor which was initially uncharged. Okay, so we have a capacitor here which is initially uncharged, and we use this voltage supply coupled together with a resistor to charge up this capacitor. Which of the graph shows correctly the variation of the potential difference across resistor R with time after the switch S is closed? So they are interested with the variation of potential difference across the resistor, not across the capacitor. Okay, this is across the resistor after the switch is closed. Okay, so if you have been following closely what we have learned in class, you know that if we are charging up a capacitor, then the voltage across the capacitor will be slowly increasing and reach a asymptote, which we usually call it as V0. Okay, then we know that the power supply here will be supplying a constant voltage as time passes. Okay, we always assume this V0 here to be constant, something like this. Okay, so what happens now is you have to understand the fact that this V supply here, which we call Vs here, at all time, Vs should be equal to Vr plus Vc if it's an RC circuit. Okay, this is an RC circuit means that it has only resistance and capacitor. So if you supply, let's say 10 volt through this power supply, this 10 volt have to be shared completely by the capacitor and the resistance and the resistor, because there's only a capacitor and a resistor, and these two components have to take up all the energy being supplied by the power supply. So let's say here can be 6, then here will be 4. Let's say here is 9, then here will be 1. Okay, no matter what, if you sum up the potential difference across C, you sum up the potential difference across R, you find that they are equal to the power supply voltage. Okay, with that said, I think it's quite obvious what we should do after that. We know that this is our graph of voltage against time. You know that at all time the power supply is constant. Okay, let's use yellow for power supply. If you are aware of the fact, if you know that the capacitor is actually increasing in terms of voltage, this is VC, then you know that Vs minus Vc will be equal to Vr. Okay, this can be obtained by shuffling a bit the equation. Vr will be Vs minus Vc. So if you know that, we can take all points, let's say we can take this point minus by this point, then we slowly we find it for every single point, then you see that the potential across the resistance will be dropping with a shape something like this. This is Vr. Okay, if you are not sure, I try to take this point Vs minus this point Vc. Okay, then you can take this point Vs minus this point VC. Take this point VS minus this point VC, and you slowly see that this will be equivalent to this pink line that I've drawn over here. So this will be the potential difference across the resistor as time passes during the charging process. So we can find that this answer is similar to this third graph, this graph at C over here. Okay, so we can see that the potential difference across the resistor actually decreases with time in an exponential fashion. Okay, you can make sense of it like this. If you are charging up the circuit, as time passes, there will be less and less charges flowing in the circuit, because most of the charges has arrived at the capacitors to be charged, to be stored, so there will be less and less charges moving in the circuit. Or you can think of it as it's getting more and more difficult for you to move a charge to the positive plate. Okay, when it gets more and more difficult, there will be less and less charges moving in the circuit, so we say the current is reduced. So if you say the current is reduced from VR is equals to IR, V is equals to IR, since you know that current is reduced, R is constant, then we know that the voltage or the potential difference across this resistor here should actually decrease as well. Okay, so this is the graph that fits the situation, because all the other graphs here are actually either constant or increasing with time. So answer is C. That's all for question 22. Question 23. The figure shows the circuit used to charge and then discharge a capacitor C. So as you can see in the diagram here, I have a capacitor C, and this circuit here is used to charge and then discharge this capacitor. So how are we going to do it? When the switch S is first connected to X at time t equals to 0, so what happens is if you connect the circuit at X to S, say let me draw it, let's say like this, then when you're connected to X, what happens is you are charging the capacitor. Okay, and then to Y at time is equals to T1. So when time is equal to T1, you switch the switch here. Before that is connecting X and S, then now you change it to connect between S and Y. And later, the circuit will be connected like this. So now the battery is no longer connected to the circuit. The battery is no longer in the circuit. So this will be a discharging process. The capacitor is actually discharging through the resistor that it is connected to. Okay, when you are connected to Y, then it's a discharging process. Okay, so if you look at the question, which of the graphs show correctly the variation of potential difference V across the resistor with time t? They're asking for the potential difference across the resistor. Okay, if it's across the resistor, it's slightly a bit we learn usually is the potential difference across the capacitor, but now they are asking for the potential difference across the resistor. But I still think it's within your capability to do so, so let's try to think how. Okay, so we know that when it's connected to X, it's from time equals to 0 to time equals to T1. Once it reaches time equals to T1, then it will change to Y and it will become a discharging process. So I believe for the time, we should probably split it into two phases. The first phase is from time equals to 0 to time equals to T1. Then the next phase will be time equals to T1 until they didn't mention until when. Okay, so the first part of the first section here should be a charging circuit. So when you're charging, then there will be charges moving from towards the capacitor to be stored. Okay, if you really look at the capacitance, if you look at the potential difference across the capacitor, okay, looking at across the capacitor, that is not what the answer for the question asked for. But let's say we look at the potential difference across the capacitor. Then it should be a charging shape, which is something like this. But since we are finding it for the resistor instead, we know from a previous question just now that the V supply should be equal to VR plus the V of the capacitor. So in this case, we know that VR is just taking Vs minus Vc. So in that case, we know that the voltage or the potential difference across the resistor should go in the opposite shape to the potential difference across the capacitor. So this should be represented by this green line over here. Okay, so this is not what we want. This is called voltage across the capacitor, but it's not what we want. What we want here is the voltage across the resistor. Okay, let's continue. Now it's connected to Y and now it enters a discharging process. If you are entering a discharging process, what will happen to the capacitor? It will drop first drastically, then slow down towards an asymptote again. So this time the asymptote is V equals to 0. So the capacitor is discharging. So now you might be tempted to draw the VR in an opposite shape. So what you might draw something like this. Well, no. Okay, why is it no? Because this equation here is no longer being applied. Why this equation is no longer valid? Is because there's no power supply in this situation anymore. There's no power supply. Okay, so essentially you have to use other means to determine the voltage across the resistor. Okay, so the voltage across the resistor, actually you can think of it like this. If I have ignored the battery over here, this pi is already ignored, and I look solely at this loop over here, you see that the charges will be, the positive charge will be flowing from this positive plate, move downwards back towards the negative plate, trying to discharge the capacitor. So as this V is decreasing, your current is decreasing. Okay, let's draw it out. We know that based on this pink line over here, we know that the voltage across the capacitor is decreasing. So if the voltage across the capacitor is decreasing, we know from C equals to Q over V, we know that the capacitance is constant. If we know that the voltage across the capacitor is decreasing, we know that the charge stored is actually decreasing. We know that the charge stored is decreasing. We know that there's less and less charge moving out from the capacitor. If there's less and less charge moving out from the capacitor, you can think that the current actually decreases as well. Okay, so the current decreases as well. So if the current decreases, then we know that VR is equal to IR. Okay, so if I is decreasing, then the voltage across the resistor should actually decrease as well. Okay, so but what should we change here is we should actually flip the direction of the graph to be this way instead. Why should we draw it in the other side, in the other way is, if you notice just now, the positive charge will be moving this way towards the positive plate. So the positive charge will actually move downwards across the resistor. It will move downwards across the resistor. But now, once we enter the discharge process, you see that positive charge now is moving from this left hand side of the plate, moving through the loop, moving to the right hand side of the plate. So before that, the positive charge, when it's charging process, the positive charge is going downwards across the resistor. But now during the discharging process, the positive charge is moving upwards across the resistor. So there's a change in direction. Therefore, we flip the voltage towards the negative region. But it's important that we have mentioned just now that the voltage is decreasing because the current is decreasing. The current is decreasing because there's less and less charges moving out from the capacitor, since there's less and less charges being stored in the capacitor as time passes. Okay, so with that said, we know that, okay, let's keep it clear, this is not the thing that you want, BC, this is wrong. So we know that the answer should be a combination of these two green lines over here. So the answer would be B. Okay, so that's it for question 23. Question 24. A capacitor of capacitance C is charged through a high resistance R until the charge in the capacitor is Q0. So it's very clearly stated that this is a charging process here. Okay, then they ask which of the following gives the current in the circuit after a time t from the start of the charging. So they are asking for the relationship of current with time. Well, this is part of what we learned in the syllabus. We know that for current, during a charging process, the current should actually drop with time, something like this. Okay, the current drops with time because as time passes, it gets more and more difficult to push the positive charge to the positive plate. When it gets more difficult, then there will be less and less charge moving, trying to get to the positive plate. Less and less charge moving means by the current actually decreases. Okay, so this graph here can be expressed using the formula I equals to I naught E minus T over RC or CR in this case. Okay, but I don't think we see any equation that looks similar to something like this. The behind part is okay, just that I naught here, this I naught need to be expressed in different form. Okay, so what form is available here? We know that I naught is it's usually related to Ohm's law. Okay, so you can think of it as the voltage across the resistor equals to IR. Okay, you can think of it this way. Then this will become I naught, and this will be voltage across the resistor divided by R. So now you can change the equation to be something like this. You can change it to VR across R, VR over R, E T over CR. Okay, of course this voltage across the R here is the initial voltage, because this I naught here it's initial, so it should be based on the voltage across the resistor at the initial stage. Okay, so I believe the initial stage, the voltage should be something like this as well. Okay, so VR initial. Okay, but we also know that VR initial here, since we know that for charging circuit, Vs is equal to VR plus Vc. At initial situation, there's no charge being stored at the capacitor. Okay, initial situation, there's no charge being stored at the capacitor. Okay, so what will happen is V across the capacitor should actually be 0. Okay, Vc initial should be equal to 0 because Q is 0. There's no charge at the capacitor. So in that case, we know that Vs initial, Vs will be equal to VR initial. And that's what we write here. Okay, but for the final situation, there will be no current in the circuit. Okay, no current in the circuit because the capacitor is fully charged. When the capacitor is fully charged, the charge can no longer move to the positive plate. In that case, the positive plate has many positive charges, which is repelling other positive charges from trying to reach the positive plate. So now it's no longer possible for the charges to move, so the current will be equals to 0. Okay, so we know that at this situation, when current is equal to 0, the VR final will be equal to 0. Okay, because we know that VR is equals to IR. So if I is equal to 0, then VR will be equal to 0. So for this case over here, we can say that the voltage supply will be equal to the voltage across the capacitor final. Okay, so why do I explain all this is I'm trying to show you that VR initial, the voltage across the resistor initial, is actually equal to the voltage across the capacitor final. So you can change this to become VCF over R in negative T over CR. So this is the voltage across the capacitor at the end, final. Okay, we know that this VCF over here, it's a fully charged state. So when it's in fully charged state, we know that you can express the relationship between C equals to Q over V. So in this case, our VCF should be equals to Q final divided by C, which is constant. In that case, we can change our equation here to be Q final, but you can call it Q naught because you know for a charging process, the voltage across the capacitor actually increase until it reach this point, which is V naught, and of course we know that the charge will move in a similar fashion. The charge, how it change with graph, with time is something like this as well, or charging circuit. So Q final is actually just Q naught. Okay, Q naught over CR. Okay, I'm substituting what I have here into here. So we can see that the equation is now formed. Our answer will be Q naught divided by CR e to the power of negative T over CR. So this is how we derive the expression to describe how the circuit current changes with time from the start of the charging. Okay, so that's all for question 24, and that wraps up our discussion for chapter 2 revision quiz set 1. Thank you very much.